Okay, hello everybody. Welcome back to Algebra. Today we are looking at revision. Can you just let me know, am I coming in loud and clear? Oh good. Now, I've noticed in the background my dog is joining me today. So let's see what the dog do. It might be the most interesting part of this lecture. Anyway, on Monday, I asked everybody here, would you like some revision? And a lot of people said, yes, I would love some revision. So this is what I'm doing today. Now I'm going to concentrate on the algebra questions. And I also have a YouTube video for the calculus questions, but they are from last year. So let me share my screen with you and we can have a look at some of these questions. Just to remember, you have lab test 1 next week. So these questions that I'm going to talk about today are all lab test 1. So Sophia, I just printed these questions out. Every time you look at a practice test, the details change. So my test will look slightly different from your test, but the nature of the questions are the same. Okay. All right. So let's start by doing some simple questions and we'll move through to the slightly more challenging questions. All right, so let me know what's going on in the chat. If you have questions, comments, observations, then let me know. Okay, first question. We have 3 points, A, B, and C. And we're asked to compare the vector AB with the vector BC. And the question is, are they scalar multiples of each other? That is the question. And then there's a second part where they ask you about whether the points A, B, and C are collinear or not. So one strategy for this problem is to compute the vector from A to B, compute the vector from B to C, and then compare them. That's essentially what they want you to do with this problem. So let's consider the vector from the point A to the point B. Now, to compute a vector from a point to another point, you look at the difference between the position vectors. Okay, this is the position vector of B, and this is the position vector of A. So we work in a component or entry-wise fashion with normal arithmetic. 4 minus -1 will be, oh, hang on, did I write that down correctly? Let's just check that. So that will be 5. Okay. So now let's compute the vector from B to C. So this will be the position vector of C minus the position vector of B. So again, quite simple calculations. 8 plus 1 is 9. 9 minus 4 is 5. Now, the question is this and this vector, are they scalar multiples of each other? That is the question. So I can see a few people on the chat are saying no, right? You can't, although you can multiply 3 to get -6, you multiply by 2, of course, you can't multiply by this number by -2 to get that number. So we would say that AB is not a scalar multiple of BC. And so you would say here you would have a little click down list, and this would be is not a scalar multiple. And so what can we conclude? We conclude that the points A, B, and C are not collinear. Okay, so those things will drop down when you're just doing the exam or the practice exam. So they're not scalar multiples of each other. And A, B, and C are not collinear. So in other words, they do not lie on the same line. All right, well, that's an entry-level question. Pretty easy. You would probably do this a lot faster than what I've done it. Let's move on to something slightly more challenging. All right. So here is another question. And you're given 3 points. And a little bit of information about the vectors joining some of those points. Okay? You're told the initial data is that you've got a shape formed by 4 points, A, D, B, C, in the cyclic order, such that you have a parallelogram. So I'm going to draw a model, and you're asked to compute the position vector of this 4th point D. You have 3 of the points, but they're asking you for the 4th point. So here's a basic model. And when we cycle around, we want to have the labeling in this order. Okay, so I'm going to put in the origin here. It doesn't matter where you put the origin. And what I'm hoping for is to compute this position vector. Okay, so this and this are equal, this and this are equal, and they're also parallel. Okay, so with a parallelogram, you know the opposite sides are equal in length and they're parallel to each other. Okay, so this side and this side, the vectors are parallel and the same length. Okay, so what we would like to do here is to compute the vector OD. And one way of doing that is breaking it down into the vector from O to B, and then the vector from B to D. Now I don't know what D is, but I know this vector must be the same as this vector. Okay, that's an important point. So I'm going to use the triangle law to get me from O to D. Firstly, go to B and then BD. Now, because the opposite sides are the same length and parallel, I can write the vector BD as the vector from C to A. Now, what do we have up here? This is almost CA, it's AC. So I can write this in the following way. Okay, because if you change the direction, you can just put in a little minus sign. Yeah, Neelan, for these, it's a really good question. Thank you for asking. They will usually tell you the order with these kinds of questions. In this style, the order will be, I think, mentioned to you unless it's a different style of question. Okay, so the vector from O to B is just this. And the vector negative AC, well, that's just this. So we want to simplify this now. Okay, so we've got something like, let me just push that over a bit. 8, negative 16, and 16. So you would go to your box and just write that in as a vector. Correct, John. It will not change. So clockwise or anti-clockwise, it will not change. Very good question, John. Harish, how is that? So, Las Yazri, that's a good question. Thank you for asking. We wanted the vector from C to A, right? That's the same as this vector. We had the initial data of the vector from A to C. So to get this, we can just change the direction and put in a sign. Does that make sense? Wonderful. Now, a question to everybody out there. Why do we have this information? Have we used anything like that? I don't think so. Yes, Max. Megan, you don't need this information in the solution that I've provided. So just be careful. Sometimes you will be provided with extra information and that will not be used. Absolutely, Liam. There are other solution methods that you can do here. One strategy is to not actually draw the origin and compute this vector and compare it with this vector. And, you know, D is like, I don't know, you let D be X, Y, and Z, and you want to find the components. So that's quite okay. Yeah, Liam, so thank you. All right, so you can definitely see the ASMRs working on my dog. Nicola, Yoshi will be coming back soon. Don't worry. I have to update my plushies. I've got a four-legged plushie over here at the moment. All right, let's continue. All right, classic example. We've seen these kinds of problems in lectures. You've probably seen them in your course pack and tutorial questions. You've got 3 points, and then you are asked to compute the position vector of a point T. And that point T lies between the point A and B such that this holds. So let me draw a little model here. Here's a line segment joining AB. And if I indicate the point T here, this ratio, or this length here, is 5 times this length here. That's essentially what this is saying. So to compute this, let's draw in some of these vectors. This is what we want. Okay. We can get a T in terms of the vector AB. So really, we want the vector from O to T, and then the vector, well, in terms of OA plus AT. But we don't know what T is. So let's see if we can get a T in terms of AB. All right, that's the basic strategy. Okay, so I can use purple. So by the triangle law, this plus that, right? Now, I don't know what T is. That's what I want to find out. But I can write AT in terms of AB. Okay, that length there is 5 times that length there. You can kind of think of it like a ratio. If you're a bit worried about where that came from, don't worry. Let me write this in another way. So the vector from A to B is this vector plus this vector. Okay, and TB is just AT divided by 5. So we add these two up. And then rearrange. So what we've done is put that in there for AT. Now a lot of students get confused with that step, so I've put a couple of extra lines in there. Okay, so let's compute AB and we can work out what our final answer is. So it's the position vector of B minus the position vector of A. Okay, so let's work component-wise. And we should get this. Okay, so position vector of A plus 5 on 6 times the vector we just calculated. Oops, that's 5. Okay, so you simplify your calculations here, and according to my calculations, you'll get something like this. Now, it is important when you enter your final answer into the Mobius box up here that you enter it as an exact value. You don't want to put decimals in. Okay, so if there's a fraction like this, just write it in 19/6. Remember, Mobius will simplify your expressions, so they don't have to be in the simplest form. Absolutely, Nguyen, you can do that. There's another way of solving this. You can let t have t has the coordinates x, y, and z, and you can go and solve it. Of course, in fact, I think I have a YouTube video about that where I use this method. So it's completely up to you. Okay. Let me have a look through some of the other questions. Okay, I might do a question on lines now. So let me just grab this. Let's see how Puppy's doing. Oh, rolled over. Oh, Annalisa, let's do that. Let's do that one. That's a projection one. Yep. Here's one. So let me discuss this one, Annalisa. So Annalisa, do you pronounce the E on the end of your name, or is it just Annalise? Annalise. Okay, cool. All right, here is a question about projections. We've got 3 points and 2 vectors. Calculate the quantities below. The projection of AB onto AC and the length of the altitude through B in the triangle ABC. So let's draw a basic triangle here. Okay, so you know me, I like drawing pictures when I can. And let's join them. Okay, so what the second question is asking you to do is to compute this length here. So let's say we have a point P there. We don't know what it is. And in fact, this question, this model, this picture is related to the first question too, because the vector from A to P will be the projection of AB on AC, and that's what they're asking for. Okay, so what do we need? We need okay, this is the vector projection now. Okay, so we need the dot product. Divided by the length. So this is the scalar projection multiplied by a unit vector in the direction of the vector AC. Now, you can combine this with a squared, that's fine, but I like to break it up because it helps me understand what's going on here. Okay, so let's compute the dot product. So we have AB up here, AC here. So what's the dot product going to be? 4 times -2 plus 0 times 2 plus -1 times -1. So it's going to be -8 plus 0 plus 1. Okay. So let's compute the square of the length of AC. So to do that, you just square the components and add them together. Okay. So let's simplify now. We'll have -7/9 times the vector AC. So all you have to do now is simplify and put it into the box. Okay. All right, the second part, the length of the altitude. So here we're hoping for the length of BP. Cirrus, no, that's a very good question. Thank you for asking. All we really want is the length here. We don't need to find the point P. It's not necessary to solve this problem. But if you wanted to find the point P, can anybody suggest how you might find the point P? Because remember, what we just calculated up here was the vector AP. Yes, James, you're definitely going in the right direction there. No pun intended. All right. So BP is going to be the length of AP squared minus AB squared minus AP squared. Okay. So you have the length there. You can compute it from the given information. You've computed AP. You can find the length of that, and then you just use Pythagoras. Okay. So Annalise, does that point you in the right direction? A lot of students have problems with the projection, but if you draw a picture and you work slowly and carefully, it's not too difficult, really. Big thumbs up. Okay, so I'll leave that for you to do, but that's the idea. Okay, I would like to do a question on lines. So let me Varshini, it's a good question. Have a look in the comments section to see if anybody can suggest how you might find the point P. It is important to read the comments, pay attention. Okay, let me have a look here. Ah, yes. This is a great question. Now, this is not a difficult question, but students seem to have some trouble working out what's going on here. So when the solution is revealed, it's actually quite straightforward. Okay. So in this question, you're given a line with a parametric vector form. Here, we're working in three-dimensional space. And then you have a plane in Cartesian form. And the question is, find the value of the parameter lambda at the point where the line and the plane intersect. So if I was drawing a picture here, this might be part of your plane. And then you have a line that comes down and touches the plane at one point. And you're looking for the value of lambda that will give you that particular point. Let's call it P. Okay, so students find this question rather difficult because they're not quite sure where to start. Now, if I write these equations out in the following form, sometimes it looks a bit easier. Okay, so we would like to find out when this and this are equal. So what we can do is substitute x in here, y in here, and z. Well, there's no z's, but you could do it. And then work out the precise value of lambda. I just woke my dog up. There should be just one value of lambda. Okay. Okay. So sub it into the equation. So it's 2 times x. Now x is 3 minus 4 lambda. Y is negative 4 minus 2 lambda. And z is this, but we don't have a z there. So what we would like to do is now expand and simplify and make lambda the subject. So lambda equals something. So let's simplify that, and we can expand each of these parts. So negative 14 lambda on this side, and negative 6, is that right? Yes. So if we bring the negative 6 over to the other side, we'll get this. So lambda equals 1. So what is the value of the parameter lambda at the point where the line and the plane intersect? The value will be lambda equals 1. Again, not a difficult question, but it's hard if you don't know where to start. Okay, this was a question involving a line and a plane. So let's continue with lines and planes. Let me have a look here and see if I can find another question. I'm just flicking through some of the pages. This is a good one. Okay, it's a little bit cut off, but I'll explain the situation to you. The plane passing through these 3 points can be expressed as a parametric vector equation or in parametric vector form using this notation. Now, remember here, V1 and V2 are vectors that are parallel to the plane and not parallel to each other. The vector A is a position vector of any point on the plane. It could be the position vector of this point, for example. Okay, you're given that one of the parallel vectors is this. Find suitable vectors A and V2 and enter them in the boxes below. Okay, so it's very easy to get the first part. We could just take the position vector of any of these 3 points, but I will take it to be the first point. So that's very easy. We'll just enter that down here. Now, what about the second vector? This is a little trickier. This is a little trickier because you don't want to produce a vector that is parallel to this given vector. So can anybody suggest what we might do for this question? Anyone? Yes, Jarvis, excellent work. Excellent work. If we compare this vector with, say, the vector from A to C, then we actually get V1. So if we make a little comparison here, going on Jarvis's observation, let's just check this. So the vector from A to C is this difference. And you'll see, oh, 2 minus 2, that's 0. -1 minus 4, -5. -4 minus 4, -8. So this given vector is the vector from A to C. And as Jarvis has pointed out, let's think about the vector from A to B. That's certainly a vector that is parallel to the plane because these 2 points are in the plane or contained in the plane. So let's see what happens with this vector. So okay, and we will just do our term by term or entry by entry calculations. Now the question here, Agna, that's a very good question. Thank you for asking. We just looked at some of the connections between the 3 points here. So I was thinking, well, if I wanted to build the equation of a plane out of these 3 points, I can compute AB, AC, BC, and so on. It just happened that the first thing we looked at was exactly the given information. Okay? So it took a little bit of investigation, Agna. Does that make sense? Manas, that is a great question. Let's check. Let me choose some pink here. We have a vector here and a vector here. Are these vectors parallel? Manas and Harish say no. Megan and Jennifer also say no. You cannot multiply this by a scalar to get this. And well, Vanch, that's a good question. You could choose the vector from B to C. That would be completely correct. So the answer here needs to take a variety of answers, just like we could choose at least 3 points for this first answer. Okay, Vanch, so don't worry, you could compute the vector BC and that would be 100% correct. Okay, as long as this vector and this vector are not parallel, then we can use both of them. And we're really only interested in this second vector. Yes, Adit, an infinite number of vectors would work. Jumeir, yes, there are infinite number of answers. Okay, so I would put this in here and this in here. Ryan, yes. No, these are separate. A, V1 and V2, they're all independent of each other, Ryan. So although I chose this, you could choose any of these points or any other points that satisfy the equation. Okay. So that's a question about planes. Let me keep looking here. Okay, let me find one more. Yes, this is a good one. Okay, last question. The plane has a Cartesian equation given by this, and it can be expressed in the parametric vector form, so PVF. You were given, oh, hang on, this is very similar to the question before, but let me do another one just so we can understand what's going on here. So you're given a V1 vector. You're asked to come up with a position vector to any point on the plane and another vector that is parallel to the plane. Okay. So one of the strategies I've been showing you is to convert to parametric vector form. Okay. And so I'm going to let x1 be lambda 1 and x3 be lambda 2. Now, why did I make those choices? Well, I'm glad you asked. The reason here is when I rearrange this equation with these settings, it's very easy to get the x2 on its own. So if I label this, it will be 10. Move that around, move that around. We have x2 on its own. So x1 was put in to be lambda 1, x3 lambda 2. So with this information, we can write our x1, our x2, and our x3 as a column. Well, Amy, what do you think? What do you think if x2 had a different coefficient? Tell me your thoughts, Amy, in the chat. So here we are. We would break this up into 3 vectors, and that will give us our parametric vector form. Now look, that is the same as that. So that's pretty good. I'm liking this. So, Manas, I think you're absolutely correct. So if there was a coefficient there, you could divide it out when you move everything around. So what could A be? Well, A would be 0, 10, 0. 1, 1, June. Can you see it? 1 lambda 2, 1 lambda 2. Let me know if you can't see it, June. June, are there any lambda 2s here? Are there any lambda 1s there? No. That's why you have a 0 here and a 0 there. I think you just got it. Wonderful. No problem, John. Okay, so I think the standard technique for this one's quite easy, but we did make a specific choice, making the simplest substitutions possible. Okay, so you would just put these into the boxes, and there you go. Okay, well, let's check on dog. Fast asleep. Are you still awake? Well, we have 1 minute, so let me know your thoughts, comments, questions, observations in the chat. I'm not sure if I can keep this up every week, but it's been fun. Without taking the pens off and like the lids off and on my pens. Let me know if you can hear that, or the rustling of paper. There. Thanks, everybody. Really enjoyed it. Ah, yes, Jethro. Let me put that in the chat. There is a secret YouTube video that I have. Let me see. I'm just looking here on my YouTube channel. Ah, yes. So this one is from last year or the year before. Now you can also ask John Steele if he plans to do a calculus lecture, a revision lecture. Maybe he will, maybe he won't. But here's something from previous years that I think you'll find helpful. So Joshua, it's best to do the up or down with the right-hand rule. So this is the vector A, this is the vector B, and your thumb will point in the direction of the cross product. So, oh yeah, I cut myself badly. Oh no. Yeah, thanks for asking, Manas. So Joshua, vector A, vector B, the cross product A cross B will be where your thumb points. So try it, Joshua. It's called the right-hand rule. It's quite fun.